Hello all, welcome to this course on time series modeling and forecasting using R. Okay. Now again a very quick refresher as always that where are we standing in this week. So we started the last session, which was the first session in this week, by a broad idea called as co-integration, right, and there we specifically mentioned that the idea of co-integration between two vectors, let us say xt and yt. Firstly, what exactly do you mean by co-integration? But then even before that we started the session, if you remember, by developing an understanding about the term called as spurious regression, right, and there we took up multiple examples as to what would happen if xt and yt, even though they are not related, but the correlation structure between xt and yt or the regression model between xt and yt shows otherwise, right. So such relationships are called as spurious, or the underlying regression between yt and xt is called as spurious regression, right. And then we sort of broadened the idea by developing what do you mean by co-integration. So again, just a very quick revision kind of a thing, that even though xt and yt are integrated, so the idea of integration is what? So xt and yt are I1. So I1 means what? So there has to be some trend in both the series. So the underlying xt and yt are not stationary, of course. So both xt and yt are non-stationary since they contain some trend. But if there exists some linear combination or a co-integrating vector between xt and yt, so again if you remember, we had brought in the idea of beta vector, right, such that beta prime multiplied by yt xt. So this entire collection becomes stationary, or rather I0. Then we can say that xt and yt are co-integrated, right. And of course towards the end we studied that why exactly do we care about co-integration, and couple of examples also, right. So one simple point that we will start today's session by is to just to mention that if xt and yt are co-integrated, couple of things happen. So in the shorter run they could deviate from each other, but there has to be some long term equilibrium between xt and yt. So in the longer run xt and yt should converge. So this is the idea of co-integration, right. So now in the same spirit we will start the second session by mentioning what do you mean by error correction models, or in short ECM. Right. So in short this is called as ECM, or error correction models. So again this is a kind of an extension or a very next step to developing the idea of co-integration. So once we know that xt and yt are co-integrated, how do you deal with that? Okay. So here ECM comes into advantage, right. Okay. So firstly we will try to understand that what exactly is this error correction model. So an error correction model, or in short ECM, is a type of a time series model used to analyze the relationship between two or more non-stationary variables which share a stable long term equilibrium relationship. So again if you repeat this definition, or if you repeat these lines number of times in your mind or number of times in your head, you can understand that the idea of co-integration is the underlying idea here, right. Because once you study or once you understand that xt and yt are co-integrated, then how do you deal with such co-integrations, and this is exactly where the ECM model comes into rescue, right. So again just to repeat, an error correction model, or in short ECM, is a type of a time series model used to analyze the relationship between two or more non-stationary variables. So again when we say non-stationary, we are kind of hinting to that I1 kind of a process, right. So I1, again if you borrow some ideas from the last session, and then there we saw that both xt and yt were I1. So since they were integrated with an order of 1, and hence both were non-stationary. So two or more non-stationary variables which share a stable long term equilibrium relationship. Okay. Similarly, if two variables move together over time but can temporarily diverge in shorter spans, ECM helps us to understand and model both their long term and short term interactions, right. So again whatever is written here, or whatever you see here, kind of points exactly to the idea of co-integration, right, because when co-integration exists, there also exists a long term equilibrium, and in shorter terms both xt and yt can deviate, of course. Okay. So similarly if two variables move together over time but can temporarily diverge, ECM helps us to understand and model both their long term as well as short term interactions or short term dependencies. Okay. So of course now we will try to understand that what exactly is this ECM model like, and then how does the ECM model is actually helpful in correcting co-integration or trying to model the underlying co-integration. Okay. Alright, so firstly why ECM, right. So why ECM? So when two variables are co-integrated, now again this is just again a quick revision, that they move together in the longer run. Okay. So when two variables are co-integrated, any deviation from their shared equilibrium is temporary, right. So I'll give you a very simple example. So let's say if you have two assets, the first asset is moving like that, right? And similarly, the second asset is probably moving like this, right? So again, if you see that in the shorter run, they can actually deviate. So let's say the second asset goes like that, while the first asset temporarily might go like that. Okay. So can you see that so both the assets have created a small gap here. So even though they have a common mean, but then the first asset in the shorter term has risen, while the lower one has dropped, right? And hence you can see this gap. But eventually, if xt and yt, or if these two assets are co-integrated, what would happen in the longer run is that again they would converge to the mean. So the first asset has to drop back, and then the second asset has to sort of rise. Okay. So in the shorter run, one can actually capture some deviations, but both xt and yt, or in this example both these assets or both these examples, share a long term equilibrium. Alright. So any deviation from their shared equilibrium is only temporary, so or rather in a short term. So an ECM sort of corrects these deviations by adjusting the model to pull the variables back towards the equilibrium over time. So if you apply this ECM on this collection of both the assets, the error correction model, then the ECM has a tendency of pulling back the risen asset back to the mean and rising the dropped asset again back to the mean, so that both the assets again converge to the same mean. Okay. So finally, ECM is essential in areas like finance and economics because it provides a way to capture both the long term stability and short term adjustments between related time series, making predictions more accurate and theoretically sound. Okay. So in general, the ECM has the capability, or ECM has the power of modeling or taking care of both the long term equilibrium as well as short term deviations, right. And of course, by applying this ECM on this collection, so predictions would be superior, forecasts would be superior, right, and estimations would be more accurate and theoretically sound. So this is exactly why we require ECM, right. So since xt and yt are co-integrated, in shorter time spans they have a tendency of deviating from the mean. So if you apply an ECM, or rather a proper ECM, then ECM has a tendency of pulling back both the series towards its mean, such that they sort of retain their long term equilibrium. Okay. Alright, so firstly how ECM works, right. So an ECM separates changes in a variable into two things, so short term effects and long term correction effects, right. So since ECM has the capability of capturing both the short term deviations and the long term sort of equilibrium or deviations, then the first thing that ECM does is the ECM separates changes in a variable into two aspects. So the first one is short term effects. So what exactly mean by short term effects? So short term effects means that captures the immediate impact of changes in related variables, right, in a shorter time span. And on the other hand, long term correction. So long term correction adjusts for deviations from the equilibrium relationship, pulling the variables back in line in a longer time. Okay. So again, as seen before, so let's say the first asset is moving like that downwards, and suddenly it deviates from the mean, while the second asset is moving parallelly with the first asset, but then just in the short term it can deviate. So let's say it drops, so a gap is created, which is this one. So if you sort of model this collection using an ECM, right, so ECM again, as discussed earlier, has a tendency of sort of pulling both the series again back towards the mean, and then by correcting that short term gaps. Alright. Okay, so now we will understand, or we will try to delve deeper into the ECM kind of characteristics of ECM and the structure of ECM. So what exactly are the key components of ECM, right. So the first term is called as the error correction term, or ECT, right. So the first component, the first key component under ECM is ECT, which stands for error correction term, right. And what is the role of ECT? So ECT simply measures the gap between the current value and the long term equilibrium value. Okay. So ECT is nothing but, so let me go back a slide since we have already drawn the plot there. So ECT, what ECT does is ECT measures the gap between short term deviations and the long term equilibrium value. So here the gap between the long term mean and the short term deviations is nothing but the gap between these two peaks and the long term mean, right. And this is exactly what the ECT does. Okay. This is exactly what the ECT does. So ECT measures the gap between the current value and the long term equilibrium value. So in other words, if the ECT is large, the model will make a larger adjustment in the next period, right? And similarly, if the ECT is small or not that large, the model will make smaller adjustments in the next period, right? And at the same time, you have short term coefficients. So, what do short term coefficients tell you? So, short term coefficients show the immediate effect of changes in one variable on the others without needing to consider the equilibrium relationship. Okay. So, on one hand you have the ECT term or the error correction term, which measures the gap between the current value and the long term equilibrium value, and on the other hand you have some short term coefficients which show the immediate effect of changes in one variable on the others without needing to consider the long term equilibrium relationship. Right. Okay. So, we will start with a small example. So, let us say suppose you are modeling the relationship between inflation and interest rates. Okay. So, let us say we want to model collectively the relationship or the interdependency between inflation and interest rates, which tend to move together in the longer run. So, in this regard, an ECM would allow us to model the short term changes in interest rates based on recent changes in inflation. Okay. So, the first point is the ECM would allow us to model any short term deviations or short term changes in, let us say, interest rates based on recent changes in the other variable, which is inflation, right. And second point is the ECM would also allow us to capture the error correction process, where a high interest rate could slowly adjust downward if inflation is low. So, again just to summarize, this slide takes up a particular example, a concrete example from economics, let us say modeling the relationship between inflation and interest rates, and particularly tells us that how the ECM comes into play here. Right? So, ECM can sort of control two things here. So, ECM would allow one to model any short term deviations between the two variables, so interest rates and inflation, and also to capture the error correction process, wherein a high interest rate could slowly adjust downwards if inflation is low. Okay. So, again similarly to the last plot, so let us say this is the interest rates, right. So, let us say I will draw a hypothetical plot. So, interest rates are rising and again they are kind of stagnating here, and let us say inflation is behaving like that in a horizontal manner, right. So, here since the interest rates and inflation are co-integrated, assuming, so what the ECM would do is ECM would correct all the short term deviations and would ensure that the interest rates would drop back to their means, which would be sort of closer to the inflation values, right. So, ECM would cover both the short term deviations as well as try to control the long term equilibriums. Okay. Okay, so now paying attention to what exactly the ECM equation structure looks like, right. So, let us say again if you have two variables, for two variables ECM involving two variables, let us say xt and yt, the model or the ECM model can be expressed as this. So, on the left hand side we have nabla yt, on the right hand side we have couple of coefficients, so alpha, beta and gamma operated on different variations of xt and their lags and yt and their lags. For example, alpha into beta into xt minus 1 minus yt minus 1. So, these two are lagged variables of xt and yt, plus another constant gamma applied on nabla of xt plus a usual random error. Okay. And here nabla is the usual differencing operator, this term that you see inside the bracket. So, beta into xt minus 1 minus yt minus 1 is the error correction term. And why exactly? So, again can you visualize that this gives you the difference between the two series at one prior lag. So, xt minus 1 minus yt minus 1. So, this sort of captures the short term deviations between xt and yt. And of course, you have this extra coefficient for some shifting here and there, right. So, this extra beta sort of gives you some room to play around with, right. But this entire term that you see inside this bracket here is called as the error correction term, which we discussed a couple of slides back. So, this is nothing but the ECT, which represents the deviation from the long term equilibrium at time t minus 1. Similarly, what is alpha? So, alpha is the speed of adjustment coefficient which adjusts yt in response to deviations from the equilibrium. So, alpha kind of takes values, and alpha tells you how swiftly or how slowly the two series should come back in the longer run. So, if xt and yt deviate drastically in a shorter term, so one can actually put a higher value of alpha or lower value of alpha similarly to again bring both the series xt and yt together in the longer run. Okay. And wherein gamma is the short term coefficient. So, the gamma coefficient that you see here captures any short term deviation. So, in general you have three coefficients, so alpha, beta and gamma. So, this beta is attached to the ECT, this alpha is the speed of adjustment coefficient, and gamma is nothing but the short term coefficient. Okay, and this is the ECM equation. Okay, so a bit more on the variables. So the first idea or the first aspect or the first component in the equation we saw earlier is the error correction term or the ECT, right. So what exactly is the role of ECT? So this term represents the degree of disequilibrium at time t minus 1. So if the value is high, it means the series is far from equilibrium, requiring larger adjustments to move back to equilibrium in the next period. Okay. So similarly, again if you go back a slide very quickly, so this term gives you the ECT. So if the value of this ECT is large or value of this ECT is high, it sort of points or it sort of indicates that the series is far from equilibrium, requiring larger adjustments to move back to its mean or to move back to its equilibrium in the next period. Okay. And then the next thing is alpha. So alpha is the speed of adjustment coefficient. So this alpha determines how quickly the system corrects back to equilibrium. So it sort of captures the speed of how slowly or how quickly the two series again come back to equilibrium. Okay. So clearly a higher value of alpha indicates faster adjustment, while a lower value of alpha suggests a slow correction process. So by the way, the first point is pointing towards this beta coefficient, right. So because beta is attached to that ECT, right, and then second point points to alpha. So alpha captures the speed of adjustment. So a higher value of alpha means faster adjustment, a lower value of alpha means slower adjustment. And last one is gamma. So gamma points to short term dynamics. So the term gamma nabla xt models the short term impact of changes in x on y independent of the long term relationship. Okay. So what happens in shorter durations or what happens in shorter time spans is captured by this term, which is gamma nabla xt. Okay. And by the way, this gamma nabla xt is independent of what goes on in the long term, because for controlling the long term behavior, we already have beta in alpha with us, right. So there should not be any mixing between gamma and either alpha or beta. So gamma is focused on short term, while beta is focused on long term, while alpha is focused on how slow or how quick the adjustment is taking place. Make sense? So a bit more kind of understanding about all the variables which are alpha, beta and gamma. Okay, so now the next thing is interpretation. So the first component is ECT or the error correction term. So if ECT has a significant coefficient, right? Now again, what exactly is the coefficient here? So the coefficient is nothing but beta. So if the ECT coefficient beta is significant, it means YT adjusts to bring the system back to equilibrium whenever it deviates. Okay. So the first component is ECT. So if the coefficient attached to ECT, which is beta, is significant, it sort of tells you that YT adjusts accordingly to bring the system back to equilibrium whenever it deviates away from XT. Okay. And the secondly, short term coefficients. So if the short term coefficients, example gamma, because gamma are nothing but the short term coefficients. So if all the short term coefficients in the ECM are significant, it suggests that changes in X have immediate effects on Y in the shorter run. So hopefully all these individual ideas would be clear, right? I mean, beta is to capture the long run equilibrium, right, and gamma is to capture the short term deviations, and alpha is to capture the speed of the adjustment. Okay. So this is a short interpretation of what do you mean if the ECT has a significant coefficient, or what do you mean if gamma is significant, and so on and so forth, basically. Okay, so now the next thing is we'll outline a few steps to fit an ECM. So how exactly do we go ahead and then fit an ECM? So the very first thing that one has to ensure is one has to perform some tests for non-stationarity. So one can either use an augmented Dickey-Fuller or in short ADF, or similarly other tests to ensure that each of the variables is I1, right? Because if XT and YT to begin with are stationary, there is no argument of co-integration, right. So if both XT and YT are stationary individually, then there exists no non-stationarity, and we don't require an ECM there, right. I mean, one can actually model them using individual white noise processes, or if you want to put forward a vector model, then let's say VMA or something like that, right. So the very first test is to ensure that both the individual series is indeed integrated. So I1 or I2, something like that. So for that we require some tests for non-stationarity. So either ADF test or some other tests, etc. Okay. Now, the second test is test for co-integration. So, one can actually conduct a Johansson co-integration test. So, this was a test given by Johansson. So, one can actually conduct a Johansson co-integration test to determine if a co-integrated relationship exists indeed or not, right. So, once you identify non-stationarity, but even though xt and yt are integrated, that won't mean that xt and yt are co-integrated, isn't it. So, individually xt and yt could be integrated, right, but does there exist a co-integration between xt and yt, that has to be checked, right. So, the second step is once you ensure that xt and yt are non-stationary to begin with, then on top of that, is there some co-integration existing between xt and yt. And in this period, one can actually apply this Johansson co-integration test to determine if a co-integrated relationship exists. And if co-integration exists, or if co-integration is found, proceed with an ECM. Okay. So, specifically ECM is predominant with co-integrated variables only, and not just non-stationary. There has to be some co-integration, or there has to be some underlying co-integration between xt and yt for a successful ECM to run through. Alright. And now, of course, once you proceed with ECM, you have to estimate all the coefficients. So, estimate the co-integration equation to find the equilibrium relationship, usually using an OLS or ordinary least squares. Okay. And lastly, estimate the ECM with the error correction term from the co-integration equation. Okay. So, now that you have ensured that the series is non-stationary, there exists some co-integration between xt and yt, then how do you develop or how do you propose the ECM equation is of importance, right. And the ECM equation we saw in the earlier slide, right. I mean, there is, you have to estimate alpha, you have to estimate beta, and you have to estimate gamma. Okay. And once alpha, beta and gamma are estimated, you actually get the complete estimated ECM equation, which can be used to model any co-integration between xt and yt. Alright. Okay, so now the next thing is couple of advantages and disadvantages of using an ECM. So, couple of advantages here. So, the first one is ECMs combine short term and long term dynamics, providing more accurate models for co-integrated time series. So, ECM has the capability, as discussed earlier, to capture any short term deviations or long term dynamics or long term equilibriums, or rather disequilibriums, providing a more accurate model for co-integrated time series. Second advantage is that they are effective in systems where relationships drift but maintain an equilibrium over time. So, even though one can actually see or one can sense some short term deviations or short term drifts, but overall in the longer run there has to be some equilibrium. Right? And such ideas or such tendencies are very common in, let us say, economic or financial data, etc. But how about limitations? So, ECM is again not completely foolproof. So, there has to be some limitations also. So, the first limitation is that ECMs require that the variables should be co-integrated, of course, as discussed multiple times throughout this lecture, that one has to actually ensure non-stationarity and co-integration also. So, ECMs require that variables should be co-integrated. So, they are unsuitable for time series without a long term relationship. So, again, just to summarize or stress on this fact that even though xt and yt are individually non-stationary, but co-integration kind of ensures that there is some long term equilibrium between xt and yt, and the whole idea of deploying an ECM is to capture that long term equilibrium, right. So, if co-integration does not exist, then ECM is not suitable for time series without a long term relationship. Okay. And then the second one is if the model is misspecified. So, what do you mean by misspecification? So, for example, incorrect co-integration rank or including lot of coefficients. So, let us say multiple gamma coefficients, multiple beta coefficients, etc. Results can be misleading. So, the ECM equation as such is not that easy to control, right. So, there could be some misspecified models which could arrive at some erroneous results. So, couple of limitations of using ECM, but at the same time you have some advantages where co-integration exists. Okay, so now lastly, as always, we will discuss some practical examples, right, and then close this session. So, the first one is stock prices and dividends, right. So, this is one area where ECM could be correctly deployed. So, ECMs are useful in analyzing stock price behavior relative to its dividends, right, where prices might diverge in the short term from dividend based valuations, yet a co-integrated long term relationship persists. Okay. So, the first example is stock prices and dividends. So, ECMs are useful in analyzing stock price behavior relative to dividends, where prices might diverge in the short term from dividend based valuations, yet if such a thing exists, then a co-integrated long-term relationship persists, right? And as we all know by this time that whenever a co-integrated or a long-term relationship persists, then ECM is kind of very helpful. As a second example, we can talk about interest rates and inflation. So, such an effect is by the way called as Fisher effect. So, relationship between interest rates and inflation, right. So, in this period ECMs capture the long term relationship between nominal interest rates and inflation, allowing short term deviations to correct over time. And such a model helps central banks and investors understand inflation expectations in relation to interest rates. So, here the whole idea is how do you capture the dependencies between interest rates and inflation, and even further how do you capture the short term deviations between the two as well as the long term equilibrium between interest rates and inflation. Okay. So, in this regard one can actually make use of ECMs very predominantly. Right. Thirdly, oil prices and exchange rates. So, ECMs model the relationship between oil prices and exchange rates, especially for oil exporting countries. And since oil prices can temporarily deviate from currency values, and ECM can show the adjustment process very nicely, right. So, third example is between slightly different from energy markets, so oil prices and exchange rates. And lastly, electricity demand and temperature. So, this is again one more area where one can actually try to model using an ECM, because surely there will be some co-integration existing. So, energy providers use ECMs to model how the electricity demand relates to temperature changes. So, for example, short term spikes in demand occur during extreme weather, but demand typically returns to average levels following long term equilibrium trends. So, again just to summarize this entire idea, so what could happen here is that in a shorter run, let us say you have two series again plotted side by side. So, and then let us say the top one is electricity demand and then the bottom one is temperature. So, for a rising electricity demand, right, there could be a rise in temperatures also. So, for example, in summers one can have more demand for electricity. In winters where temperatures are low, one does not have that much demand for let us say ACs or fans, etc. So, as and when the electricity demand rises, the temperature also rises, but there could be some short term deviations, right. I mean, let us say even if temperature drops for a short term duration, even though the temperature is dropping, the energy demand can still go on rising. So, maybe because people are kind of using both ACs as well as geysers, right. So, there could be these short term deviations between energy demands and temperatures. So, in this regard, if one applies an appropriate ECM, so ECM would ensure that the energy demand or the electricity demand kind of converges back to the mean as in when the temperature also rises, right. So, in the longer run there will be some equilibrium between electricity demand and temperature. So, hence just to conclude this session, broadly speaking, the idea of co-integration we saw in the earlier lecture, and then the idea of modeling such co-integration using ECM or error correction models we saw in this particular lecture. Right. Now, in the subsequent lectures this week, we will delve deeper into the ideas of let us say estimation, and then a few more examples of co-integration, right, a few more tests of co-integration let us say, and down the line we will close this session or close this week by a practical session in R. Right. Thank you.